Welcome. In this video, we're going to quickly review what an irrational number is. We've worked on this for a couple days. This first objective should be familiar. It tells us today that to understand that a rational number is any number that can be expressed as the ratio of two integers. As we know from class, an easier way to understand that means any number we could write as a fraction so long as the numerator and denominator are both integers. That means an irrational number, a number that is not rational, is going to be the opposite. These numbers exist naturally in the world, but the big thing is they're so complicated we cannot express them as a fraction in the form a over b, where a and b are integers. In order for this to happen, for a number to be unable to be written as a fraction, there needs to be two qualities. It needs to be non-terminating. That means, and it also needs to be non-repeating. Pause the video and think about what non-terminating and non-repeating mean. Welcome back. Non-terminating, hopefully you understand, means that the decimal never stops. The decimal expansion continues to go. We're going to look at some examples down here. Non-repeating, this is another separate but important quality, means that the decimal doesn't have a pattern to it as it continues to never stop. So I'm just going to say there's no pattern to it or no repetition going on in this decimal that never ends. Some of the primary examples we're going to see of irrational numbers, the first one you worked with in 7th grade that you didn't know was irrational at the time was pi. Pi, we had an estimate for it of 3.14 that we use a lot of times, but the real value for pi is 3.1415926554. It doesn't stop here, it keeps going forever. It's non-terminating. And as you can see, there's no pattern, there's no repetition here. E is another natural number that exists in the world. Pi comes from the circumference divided by the diameter. E will help you when you work with exponential functions. Talk about that more in 9th and 10th grade. But E exists naturally in the world. 2.71828 is an estimate for it, but this ... this ellipses tells me that the decimal keeps going. Pause the video and think about what happens if I have square roots. Will square roots be rational numbers or irrational numbers? Welcome back. Hopefully you were saying for square roots, well, it depends. Some square roots are going to be rational. Which square roots are going to be rational? It's the perfect squares that are going to be rational. Some examples: the square root of 9, because that equals 3. The square root of 4, because that equals 2. And any of our other perfect square roots. But the rest of the square roots are going to be irrational. The reason for that: if you go ahead and put any of the square roots for integers between 4 and 9 into a calculator, the square root of 5, we see a crazy decimal that doesn't stop here. Google's calculator runs out of places. Same thing's going to happen when we do the square root of 6, the square root of 7, and the square root of 8. It's not until we get back to the square root of 9, another integer answer, a perfect square root, that we have our next rational square root. So again, for square roots, it depends. Our last question: pause the video and think about what if we have non-terminating decimals but they have a repeating pattern. An example of that would be 0.33 with a vinculum, or this little line over the 3 telling us that's going to continue and never terminate. Pause the video. Will these types of numbers be rational or irrational? Welcome back. Hopefully you realize that these numbers are going to be rational. As complicated as they are, any repeating decimal actually comes from a fraction. So they're rational because they originally were a fraction. This one, the primary example here, we should know that 0.333 repeating just comes from the fraction 1 over 3. Finally, if you take a look at the bottom of guided practice today, again, I would recommend you use this helpful resource, this cheat sheet here. It helps you understand, kind of to view visually, irrational numbers, some of the examples in this red box, and then this blue box kind of categorizes all the different types of rational numbers that exist in the world that we're more familiar working with.